Okay, good afternoon and welcome to the webinar, Considerations, Best Practices, and Energy Implications for Reopening Critical Community Facilities in the Pandemic. We're excited that you're joining us and we have a great program planned for you today. Before I get started, we wanted to run through some housekeeping items on Zoom. We'll cover questions at the end of the webinar session. As you have any questions, please use the Q&A button bottom of your screen, which enables you to ask questions to the webinar hosts and panelists. You can send your questions publicly or anonymously. Please type your questions in the box and hit send. Once your question has been sent, the host/panelists will answer your questions live at the end of the presentation. Please also feel free to use the chat feature to type a message to all panelists or everyone on the webinar. It's a way to ask informal questions or chat with other attendees. If you have any technical questions, please use this chat function to talk to us about any of these issues. Please do not use the raise hand button. If you have questions, please use that Q&A box or ask us a question through the chat. I do want to note that this webinar will be recorded and will be available to all attendees. We'll distribute the recording within 1 day of the webinar completion. Also, you'll receive an email. Thank you for participating in the event. There's a link in that message to provide feedback on the event. Please take some time, no more than 5 minutes, to provide your feedback and thoughts on the webinar. There's also an opportunity to ask for further support for your organization to investigate pandemic mitigation strategies with us. We really appreciate your feedback to improve our future events. Finally, if you're interested in CEUs or professional development credits, please email me at cassie@cdac.org, and I'll pop that in the chat for a certificate. I just wanted to note, for those who are architects and members of AIA, we're working on credits with them as well. Please let me know if you're interested in these educational credits also. Again, I will pop my contact information in the chat, and it will be at the end of the webinar presentation as well. Okay, I think we're ready to start the session. Well, we're thankful to be hosting today's important event, especially during uncertain times with the pandemic that we face. Our webinar host today is CDAC, the Smart Energy Design Assistance Center, and we're really excited to have you here today. I did want to just go through really briefly a little bit about CDAC and who we are. Really, we're an applied research program at the University of Illinois, working in collaboration with 360 Energy Group. We assist buildings, communities, all different sorts of facilities and entities in achieving energy efficiency, saving money, and becoming more sustainable. So our goal is to reduce the energy footprint of Illinois. We provide a lot of different types of services, from cost analyses to education and training, to even just quick advice. We can help you with the research to enable your energy efficiency projects and goals. So we do a lot of research, as well as advocating, of course, for a more sustainable and green future. We have a variety of different programs that we offer, and I did want to mention that if you are interested in any of the sorts of discussion that we talk about today, there are opportunities to help you and your facilities uncover COVID mitigation strategies, risk analyses, and help planning for the reopening or growth of opening of your facilities. So these are our esteemed panelists for our discussion today: Dr. Helen Nguyen, Dr. Ty Newell, and Robert Nemeth. They're all, if you could give us a wave, they're all on their cameras today. We'll first have Dr. Nguyen join us today, and then Dr. Newell, and then Mr. Nemeth as well. So as each of our panelists are getting their slides up and sharing their screen, I will introduce each of the panelists. So let me start with Nguyen. So Dr. Helen Nguyen, here we go. Sorry for that delay. I'm going to introduce Dr. Nguyen, is the Even Ratchev Endowed Professor and Chair of the Environmental Engineering and Science Program, Department of Civil Engineering and Environmental Engineering at the University of Illinois at Urbana-Champaign. Dr. Nguyen teaches graduate and undergraduate classes in environmental engineering with an emphasis on physiochemical processes for water and wastewater treatments. Her research interests include pathogens and biofilms in drinking water and distribution systems, pathogen profiles after natural disasters, and water and food safety. Dr. Nguyen is a member of the American Chemical Society, the American Institute of Chemical Engineers, and the Association of Environmental Engineering and Science Professors. Dr. Nguyen holds an MS and PhD in Environmental Engineering from Johns Hopkins University, an MS in Earth and Environmental Sciences at U of I Chicago, and a BS bachelor's degree in geology. She is a faculty advisor for Engineers Without Borders as well. And without further ado, Helen, take it away.
Thank you, Casey, and also thank you all of the attendants. I'm really glad to be able to share with you some of the knowledge that we have, we know, and it may be informative for you. So my presentation will focus on the virus that caused the disease, COVID-19, and also other respiratory pathogens, role of environmental transmission and engineering control. So I just like to remind you that the COVID-19 is a disease, and SARS-CoV coronavirus 2 is a virus that causing the disease. So you probably already saw that picture many times for SARS coronavirus 2. The important thing I want to show here is that spike protein here is pretty much everything. That's very important. Okay. So coronavirus is not new. Middle East respiratory syndrome coronavirus, the MERS coronavirus, already happened in 2018. However, it's only lead to about 2,000 cases, as you saw in this graph in here. So this virus, actually, the outbreak was stopped mostly at the border before it got into the global scale. Okay, and so the SARS coronavirus 2 has been isolated and sequenced. And so this is how people understand the dynamics of the disease transmission. So for example, this is the genome of the family of coronavirus. So most coronavirus is in this side here. However, the one that we have been suffering is the novel coronavirus. So it's in this lineage here. And the reason that people said, scientists think that it may come from bat is because there is a bat coronavirus genome that is very similar to this novel coronavirus. And however, as you see that if we sequence more genome from other animals, then we may find a host that is closer to the one that we have right now. Okay, and coronavirus, once it got into human, it starts to mutate. So this graph here to show that, so this bat genome, the genome of the isolate from bat is all the way down here on this corner. And once it get into the human in China, so you would have all of that yellow here, it starts to mutate and to all of other places. So there is no one virus. There are actually many different viruses. So the point I want to make in here is that the virus is like a silent enemy. It's doing its thing and we don't see it. It's still there. It's changing. It do everything. It doesn't really care about the border. It doesn't care who we are, where we are, what we are doing. So this is something that we want to keep in mind. So why do we get infected? Okay, so virus is not a living cells. It doesn't need to multiply outside the host cells. All the virus need is to get into a host, an animals or human. Once it gets to the host, it multiplies inside the host. Okay, And so, for example, in here, we have a person who got infected, and the virus multiplied inside this person in here. And this person is shedding the virus by different ways. So this way that it show here is mainly through breathing and sneezing, coughing, but it's also through fecal matter too. Okay, and droplet, contact transmission, aerosol, airborne transmission. All of this is very important. Okay, and so airborne SARS coronavirus 2 have been detected in 2 hospitals in Wuhan, China. Okay, so in this case here, and you see that they found it in the PPE removal room, 2 PPE removal rooms of this hospital, also found in the medical offices. Okay, so those places have no patients, but it have the healthcare providers who work in these places who remove their PPE. Okay, and so this study here was conducted at University of Nebraska Medical Center, so our neighbor here. And so the y-axis is the genomes, detected genome of the virus, and the x-axis is different type of sample that they found. So you can see from this slide here that the genome of this virus are found in all of the subject, all of the things in the hospital room of the patient, and also in the bedroom air, handling air sample and personal air samples. And very importantly, not just genome that they found, they also found that the virus recover from those samples, from those air samples or infectious. They are able to infect cells, the whole cells. So this is another data to show that SARS coronavirus should survive in aerosol up to 16 hours. Okay. SARS coronavirus also survive on common surfaces. So copper is not very friendly to this virus. Cardboard is somewhat friendly, so the virus can survive up to about 24 hours. Stainless steels, about 48 hours. Plastic surfaces is the one most friendly to SARS coronavirus. So I want you to keep in mind that, okay, it's the indirect transmission by touching could be important. Okay, even though the virus doesn't survive long time, but if dirty hands could transmit the virus, and then the next person touch onto another surface like plastic surface or something, and plastic surface pretty much everywhere. Here is another study that conducted in China. So this seafood market is the place where people found the SARS coronavirus and COVID-19 first, right? And so this is a simulation. This is a computational study that estimate the risk of infection after 1 hour of exposure. Okay, and you can see that the indoor environment, so this is the risk for the indoor environment, is much higher compared to the outdoor environment, and clearly further from the market, the risk become lower. So that just makes common sense. Okay, one thing I want to point out here is that 10 to the minus 3 is the level of manageable risk. Okay, you still have risk, but it's manageable. And this study, so this data here are at the beginning of the outbreak. Okay, so in this data here, this graph in here, the y-axis is the risk of accumulated exposure as a function of time. So at the beginning, December the 1st, the accumulated risk is on somewhere around 10 to the minus 3, right? So this is manageable. However, as with time going on, the risk accumulated. So that means that it's very important that we stop it. Or I can say that we stop it, but we reduce the risk as much as possible and as early as possible. So uh, after my presentation, Professor Nguyen will talk more about good ventilation, because as I show in here, the risk of outdoor is much lower than the risk of indoor. Okay. And in my lab, we also found that if ventilation cannot be changed, then you can consider portable air purifier. And we found 3 times reduction in microbial load just by a simple filtration-based air purifier that we just bought from Amazon. Okay. So that is about SARS coronavirus. To another respiratory pathogen that I want to bring to your attention is Legionella pneumophila. Okay, just last week, so August the 9th in here, there's a report that CDC have to close some of their Atlanta office because of outbreak of Legionella. And it actually makes sense, and it's expected that Legionella pneumophila could cause some problem after a long, a prolonged stagnation, because you know we all have to stay home. We don't go to our offices, so water is not used. So I just want to spend a few minutes to talk to you about Legionella. So this is a very smart bacteria, very, very smart. It's there all the time, especially in cases that we cannot maintain our distribution systems. Okay, so this bacteria here try to get inside biofilm or try to get into another microorganism called amoeba to escape chlorine. If you expose them to chlorine, they will be inactivated, but it is smart. It can get into other things to escape chlorine. And then it multiply itself inside the amoeba. So similar to what virus does. And then it's released. And so one is released here. If you have chlorine, they will be inactivated. But if you don't have chlorine, they may be released and cause trouble. You can choose what water you want to drink. It's very difficult to choose what air we want to breathe. Okay, and so Legionella cause it's a waterborne pathogen, but its infection is through respiratory, so it's caused lung infections. Okay, so my lab have been working on Legionella pneumophila for years already, and we did a work that we compute the annual infection risk of Legionella um, for different locations, okay, that have biofilm in the pie system for different type of scenario of stagnation. So the first one that I want to show here is that if you don't have any chlorine, the infection risk is very high. Okay, so it's about 10 to the minus 4. So the guideline from EPA, the management risk for Legionella is about 10 to the minus 4. So we only 8 times higher than that without chlorine. So in cases that you do have chlorine, but it gets consumed while water is not used, then the risk is about 2 times 10 to the minus 4 for 1 hour stagnation or 48 hours stagnation. So the prolonged closures also means that there are a lot more, there are stagnations. Okay, and so before we started working in Newmark lab, where my lab is based, then we measure the concentration of chlorine in the water, okay, in a number of water fountain in our building in here. So we found that in the best case scenario, we have to flush our water for about 1 or 2 minutes. Usually, you only need to flush your water up to about 30 seconds. You should see the chlorine level get to about 2 milligrams per liter. Okay, so that is the level that ensure that reduce bacterial growth, biofilm growth. And there is a water fountain right next to my lab, actually, that need about 8 minutes of flushing so we can start seeing chlorine concentration in there. So this is before opening, and then 1 week after opening, meaning that there are some people came back to the building doing some work, we are using the water, then we still have to flush the fountain, water fountain, for some time to see chlorine. So chlorine is not having chlorine doesn't mean that your water is not safe, but not having chlorine indicate that you have a higher risk. Okay, because chlorine is added to the drinking water to manage the risk. Okay. Another thing that I want you to remember is also that a lot of places are using the water filter that you hook up to the tap. Water filter themselves remove chlorine. Okay, so this is some data that we did before the pandemic actually. So this data here is exterior of the building. So we see that the chlorine concentration before stagnation or post stagnation is about 1 to 2 milligrams per liter. So this is a right concentration that the water treatment plant in Champagne, intend to have. For the unfiltered water, okay, and we also see a very similar picture. So the chlorine concentration is there. After stagnation, you may have to, to flush the water for about 30 seconds, but it's there. However, for the filtered water, okay, that all of the chlorine is removed. So keep that in mind. The chlorine is removed when you are using the portable point of use or water filter. So flushing water during the closure and now allow the chlorine from the fresh drinking water to get back to plumbing systems. So we did the Legionella measurements for the water fountain in Newmark building. We didn't find anything, and we are really happy about that. So if you want to get your water tested for Legionella and chlorine, you can contact the ISTC here right on campus. They have a certified lab to do that. So this is my concluding remark here. So SARS coronavirus 2 is transmitted through direct contact and indirect contact. So don't ignore indirect transmissions. Everything that we are trying, not everything, many things that we are trying to do now, for example, wearing masks and stay 6 feet apart. This is to prevent direct contact and direct transmission, but indirect transmission through air is also very important. Prolonged closure means more stagnation in water and a potential higher risk of Legionella pneumophila transmission. Remember, CDC also have the same problem, okay? So I'm not saying water is not safe. The drinking water treatment is always produce good, safe drinking water. However, because of the long, prolonged closure, you may want to avoid direct breathing exposure until the chlorine level in your building is back to normal. So this is all I have. Thank you very much.
Thank you, Dr. Nguyen. That was wonderful content and great information. Now I will introduce Dr. Tai Newell. Dr. Tai Newell is co-owner and co-founder of Build Equinox, a company devoted to inventing technologies for healthy, comfortable, and sustainable living. He retired from the University of Illinois in 2007 as an assistant dean in the College of Engineering, and having advised 70 master's and doctoral graduate students, is an emeritus professor of the Mechanical Engineering Department as well. His degrees are in mechanical engineering. He has lectured around the world on indoor air quality, comfort, solar energy, building energy efficiency, and resource conservation. Dr. Newell has been a Fulbright Scholar at the Universidad Nacional de Salta in Argentina, an Arcotaf Scholar in the European Union at the EPFL Lausanne, Switzerland, and a United Nations workshop leader in Beijing, China, an academic leader in the Tec de Monterrey Institute in Mexico, and an advisor in the USAID NZEB project in Universidad Centroamericana, El Salvador. Ty lives in a 100% powered home, or solar powered home in Urbana, Illinois, that features automatic fresh air control, 2 electric vehicles, and also 100% solar powered, and is the first home with an Illinois municipality to be permitted for rainwater harvesting use. Build Equinox is located at a 4,500 square foot Morton building in Urbana that is also 100% solar powered. Thank you for presenting today, Dr. Newell, and take it away.
Thank you very much, Cassie, for organizing this, and thank you to all the participants for being part of this. And Cassie, thank you for using a picture that's about 10 years old. As I tell people, I'm retired, but I'm not tired, and so I appreciate my attachment to the university and the important work that it does. And now I'm back on the front lines, fortunate to work with my son and another young engineer in working toward sustainable living, how we live healthy, comfortable lives in a sustainable manner. So my background's in HVAC, both research as well as on the practical side, implementing smart ventilation as far as healthy homes and air quality in homes and buildings. And for a long time, we've been studying the transmission of diseases and how ventilation systems in our buildings can either be disease incubators or disease inhibitors. And so I'm bridging from Professor Wynn's discussion of the more basic science aspects of COVID-19 disease, and then Robert's boots on the ground, and I've appreciated working with CDAC for many years and their expertise, and they've crawled around more buildings than anyone I know of. And so these guidelines will be, say, at a higher level. The reality is that then there's a lot of digging to organize and to do these things in actuality in any building. But I hope to give you some guidelines that are practical and that you can actively put together. And I hope that this gives you a peace of mind as well as the others around you in those buildings and situations that you're involved in. I don't like testing. I don't like wearing a mask, just like everybody else, but these are critical to do. And those of us that are part of the University of Illinois are very fortunate with what you may have heard of, what is the best testing system I know of in the world, where you go in within 5 minutes, you spit in a tube, and within a few hours, you get results on an app that then clears you for moving around campus and knowing in an anonymous manner whether you've been near somebody who's been infected. Why isn't this around the country? Well, that's another discussion, but that's what it should be, a very simple test. Knowledge is the ability to snuff this out. And face masks with very simple analysis. If a face mask reduces 50% of the contagion from getting out of your respiratory system into the air and on surfaces, And if we had face masks that would protect us, the N95s, nothing more than a MERV 16 filter put on your face, that again, if we could cut at least 50% or more, our probability of getting sick is reduced well below 25% of what it is without those things. And that's enough to snuff this out.
Hey, Ty, just really quick,
Yes.
your slide did not progress. So if you want to click on your next slide, I want to see,
Can you
we
see
want
that
to
one
see
progress?
that. No, we can't.
Let me see if it says I'm sharing my screen.
You are, definitely.
And there's the title, and there's the next one. Do you see that one? Or just the title?
Just the title slide.
You're seeing your PowerPoint window and not the presentation window.
Let me go back up here. So if I stop share, and I'll try to share again.
Okay, thank you.
And I'll go to presentation. And how about that? Are you seeing the second slide?
We're still seeing your PowerPoint window. It has the main slide and all your slide deck on the left side of the screen instead of your presentation window.
Ty, if you'd like, I can share your slides.
Yeah, why don't you do that, Cassie?
Okay, great. Let me get that pulled up here. Thanks for everybody's patience. You know how fun technology can be sometimes. There we go.
Especially with an old person at the helm.
Oh no, there we go. Share. We'll start your presentation.
So if we go to the second slide.
Can everybody see the second slide? Great.
Cool.
Please proceed.
Thank you. So as I mentioned, no one's enamored with testing or wearing a mask. And so what can we do about it in a practical manner? And one that's not so fuzzy, but action-oriented, quantitative, so that for ourselves and others, there's a peace of mind. And then what is the cost associated with that? And so those are what we will discuss in this part. So 3 recommendations that I think for home as well as business and public gathering spaces. First, and we'll talk about this in a little more detail, measure carbon dioxide. It should be kept below 800 parts per million. And I'm sitting in a room. I'm actually in my home, and let's see if I can get the glare out of here, but you can read that. It is about 601 parts per million. And that means that there's plenty of fresh air in this room. And that's a key determinant to knowing if the concentration of contagion, if the infectious viral particles and droplets circulating in the air have been reduced to a fraction that reduces my probability of getting sick. Also, as has been demonstrated over the past several years now, that virus-laden particulates, droplets of various sizes, that these are filterable, and they're filterable at a high level. So increasing filtration from the standard MERV 8, that's primarily to protect coil heat exchangers from dirt and debris, to at least a MERV 13, but even better, at least a MERV 11, but even better 13 or 16, that you can filter out 90% of viral particles. So whether in your main circulation system, or as Professor Wynn noted, with a small space filter air purifier, that these particles can be reduced in concentration. And then another addition would be ultraviolet germicidal irradiation. And all of these things have a lot of science and studies behind them to back them up. And we've written responses which CDAC, I think, will make available to you with citations to the studies that back these up. But ultraviolet germicidal irradiation, if you operate it with about 0.02 watts of ultraviolet, and that comes out to about, say, 4 watts of ultraviolet for 200 CFM of airflow, or about 16 watts with 25% conversion efficiency of electrical to ultraviolet radiation power, that this has a single pass kill efficiency of about 85%. And in combination with a filter, you do want both, because where a filter is also removing other particulates that you don't want to inhale, and ultraviolet gives you an additional layer of protection of killing things that are making it through, on top of fresh air just being sanitized air to begin with that dilutes. We need all three of these in order to improve our health in a building. On top of this, for businesses, public gathering spaces, schools, UV, GI, surface sanitizers have been shown to be 10 times more effective than washing surfaces. Basically, UV bulbs that are placed on a cart, and Robert will speak more about this, but that this has been shown by studies to be very effective of getting additional microbes, deactivating them on surfaces where they're hanging out. Wearing face masks is essential. It would be nice if we also had masks that protect us, but the masks, the cloth masks that simply keep us from spewing viral-laden droplets out in the air are critical to protecting everyone around us. And then when you are around somebody that's not masking out in public and you don't know them or where they've been, stay away from them, and more than 6 feet away. Think of somebody blowing a smoke ring and how far that can travel. It's 20, 30, 40 feet that this cloud of infectious particles can travel. Next slide, please, Cassie. And I don't want you to think that you have to sacrifice energy efficiency. As Cassie mentioned, where I live and where I work are net zero and 0+ buildings. My home also provides enough energy for driving about 8,000 miles in 2 electric vehicles. And our work, something a lot of people might not picture, could be net zero, a 4,500 square foot Morton building with geothermal heat pump, well insulated, good windows, and then solar to power it. This is net zero. Next slide, please, Cassie. Here's what fresh air does to us, and this is what's really exciting, is that when you think about taking, say, a special action to protect us against the current pandemic, you wonder, well, if it is effective, so we don't get it, how do we know that we would have gotten it anyway, and that all this effort, all this potential cost wasn't in vain, that we really didn't need to do it? Well, these guidelines that I'm giving you, you're going to experience a return of whatever costs you put in that's going to occur regardless of COVID. That we should be doing these things. There's a number of us have been saying we should be doing these things for decades. That is doubling airflow from the level that's the current building standard. And those of you familiar with like ASHRAE standards, 62.1, 62.2, the title of those are adequate airflow. And these are odor-based ventilation, not health-based ventilation standards. So these are standards based on only making 20% of a building's occupants dissatisfied with the air quality. And this is not healthy air, and you cannot smell healthy air. So a study by Dr. Milton, who you've seen him perhaps on TV, he's been on CBS and other national broadcasts. He was one of the co-authors of the letter to CDC and WHO saying this disease is airborne, co-signed by about 300 other scientists and epidemiologists around the world. This is airborne. We need to take this seriously. Well, he's been working on this stuff for decades, and you'll find lots of papers on various types of airborne contagions. But just studying over 3,000 employees scattered among dozens of buildings, he found that by doubling the airflow per person from about 20 CFM to 40 to 50, that sick days were reduced among 3,000 employees, a sizable number, by 40%, the same effectiveness as the flu vaccine. And the value of that 40%, roughly 1 day of sick leave per person, about $500. So a number of folks, next slide please, Cassie. So a number of folks might be wondering, well, what's the cost of that? We're going to double that fresh airflow. Now we have more conditioning needed, summer and winter. And in Illinois, for those of you here, we have the worst climate in the country. We have those Arctic blasts from Minnesota and that heat and humidity from New Orleans in the summer. So we've got quite a range of conditions to prepare for. Well, telling you that going to 40 CFM to 50 CFM per person, which is more than double of what most buildings are at now. And the simplest way to know if you're at that level is by measuring CO2. And if there's one thing out of my part of the talk to get, is to get a CO2 measurement instrument. They're $150 to $200. You can carry them around, share them, map out your building, map out your home, take them to restaurants and motels. You'll be surprised at the range you see. This tells you absolutely how much fresh air has been added through ventilation as well as infiltration and construction flaws. You'll have about 1,000 to 1,200 with about 20 cubic feet per minute per person. 800 ppm of CO2 is about 40. And it escalates. When you get to 400, you're outside. It's infinite airflow. The concentration of contagion is 0. You're very unlikely to get sick outside unless someone sneezes on you. 500 is very high, and for sure you don't want it too low because then you do start having excessive energy costs. Next slide, please. This is just a plot using something called the Wells-Riley equation, but it is for determining the probability of getting sick. And again, by Dr. Milton in another study, when he was at Harvard, that CO2 coupled with the time length that you're in a space determines the probability of getting sick. As CO2 goes up, the fraction of air that you're breathing that came from someone else's lungs goes up, and the fraction of viral particles that were in an infected person's lungs go up until finally it's highly probable you're going to get sick. Next slide, please. And here is the same plot, but translated a little differently in different cases that I've run. The upper red circle are current household ventilation standards, but with people wearing masks inside a home. Without wearing masks and without good filtration, but at current ventilation standards for a home, which is somewhat less than 20 cubic feet per minute per person, you're over 90% going to get sick. And indeed, studies have shown that 80% of a group of 7,000 people who were traced and tracked for COVID infections, that 80% of the transmission occurred at home. But that other 20% that occurred, outbreaks that occurred outside of the home, these involved up to 8 to 9 people per infection. And this leads to a conclusion that one person goes out that's infected, infects maybe 8, 9, 10 others in a public gathering place, shopping or restaurant. They go home and infect 2 or 3 others in their home. And that's one person leading to about 30 infections. That's how simple it gets transmitted when we don't wear masks, when we don't distance, when we don't have concern for others. When we take these guidelines and double the fresh air, improve filtration, as well as then add ultraviolet, we can drop down to a third of the chance, a very substantial reduction. And what happens with virus transmission is that when you get below a certain level, it will decay on its own and snuff out. But the US, unfortunately, has been bouncing around above the decay limit, and we've been unable to snuff this out as so many other countries have been able to do. Next slide, please. So just a few examples. Here's a real building, this green line of CO2, and it was from 6 measurement stations placed around a 25,000 square foot building, 120 employees, and so it looks a little bit smoother. You can see where people go to lunch around noon. In our simulation, we didn't put in a noontime change of the building populace, but the brown lines are simulation, and the blue is our simulation if it had improved ventilation. And with that, this building had about a $6 million payroll, a utility of about 90,000, which is a big utility bill for this size facility. And our study showed that by improving the ventilation, getting it down to this 800-900 parts per million of CO2, employee productivity, because CO2 and the associated human output of VOCs impairs human cognition, and at standard building ventilation levels, recent studies show by about 10% or so, and the value of that 10% productivity is about $750,000 a year, almost 10 times the utility costs. And a 1% drop in productivity per year, about 60,000 bucks, it's a big deal. And that improvement in ventilation from what they're currently seeing would drop sick days by perhaps 40% over the size of a population, another $60,000 gain. And this is without considering COVID. So we see that utility bills, while important to facilities managers, and for sure you want to run things efficiently, compared to the human cost, the human resources side of the dollar equation, this is quite small. Next slide, please. I won't go into detail on this. Here's a Department of Motor Vehicles facility with demand control ventilation. And for sure they can control CO2 and hopefully they will, perhaps are listening to this webinar and will lower their CO2 sensors to 800 parts per million. Next slide, please. Here's a church, a house of worship. People gather together, but auditoriums, concerts, other large gatherings of people, CO2 goes up. It takes an hour to get very high probability you're going to get sick if there's an infectious person in that building with you. So room air filtration, as Professor Wynn discussed, additional fresh air, but somehow this space needs to have decreased population density, spread people to other rooms, hook them in through a webinar, through Zooming. But this is ground zero for transmission. Next slide, please. You can have too much fresh air, as the library in Muhammad, which we studied several years ago, and we brought it back up. They were having trouble managing humidity, and it turned out they're basically trying to air condition the whole outside. And in adjusting their air quality, their ventilation system, so that they had better CO2, still kept to about 600 to 700 parts per million. And interestingly enough, the VOCs, which are the kind of noisy lines on that dropped down, which we suspect the 80% humidity that they had been experiencing during the summer, as that dropped down to a more reasonable and comfortable 60%, that it dried out, and humidity for sure makes things more volatile. And there is a good energy savings by this too. So for sure, having your system surveyed, either internally by your facilities folks or by others, is important. Next slide, please.
Hey, Ty, do you have, I'm sorry to interrupt. Do you have, we only have 10 minutes left and we need
Okay,
some time for Robert.
let's skip this, and you'll see this in the slides that are available to you. But it's a demo. Next slide, please, of how you can have both comfort as well as good air quality. And let me say on this slide, when you consider doubling fresh airflow, increase in filtration, and adding UV, on a cost per hour of employee or staff basis, you're talking about a penny per hour. Not a lot when you consider the value of the humans in any building. Next slide, please. And finally, this is my last slide. We need to put human resources and facilities folks together, and perhaps others, to make these decisions. When I was a project engineer doing facilities like projects, and we do a life cycle cost, typically we just look at the capital costs, the maintenance, repair, the lifetime utility, and see what had the lowest lifetime costs. When you add the employee productivity into the equation, it drastically changes. 1 degree outside someone's comfort range, a bit of humidity outside someone's preferred humidity range, dissatisfaction with air quality, and the impairment of human cognition. These are all much, much more expensive. And when a facilities has its ventilation, its fresh air or filtration or other air quality change such that it impairs people, people get sick more often, it's human resources that bears that cost. So that ends my slides. Sorry for taking so long.
Thank you so much, Dr. Newell. Such good information. And I will say that we will share these slides out at the end, and we will also have contact information available at the end of the presentation if you do want to follow up with any of our presenters further. So thank you, Dr. Newell. Awesome. Well, I will introduce our next speaker, Robert Nemeth. So let me get his slide shared here. Okay.
Thank you, Cassie. I don't need an introduction. That's fine.
Okay, well, Robert is our technical director here at CDAC. So Robert, please go ahead.
Okay, I have 4 topics that I wanted to cover, and I probably won't get through this, but the 2 most important topics I'd like to cover are risk assessment and airflow. Helen and Ty both discussed some mitigation and energy efficiency topics. So go ahead. We're going to skip over some slides here, Cassie.
Sure.
Let's start. Go back to that one, last one. I want to bring people's attention to this link to the webinar at the bottom. These 2 gentlemen provide me some of the information for this presentation. They are experts in the field of airflow and how contaminants migrate through spaces. And I would like to give them credit for their information. Thank you very much, both Mr. Smith and Dr. Kankari. Okay, next slide. So how do you do a risk assessment? Yeah, one of the biggest problems we see is people think, well, gosh, how are we going to do? How are we going to mitigate risk in our building? Well, the first thing you need to do is do a risk assessment, because your whole building may not have to be mitigated. It may be fairly safe in certain parts of the building. So what we want to do is we want to identify what spaces are at risk, or at high risk, or medium risk. So there's a spreadsheet that Mr. Smith has provided me that you can use for this, and he provided me a scrubbed version of that I can distribute if you're interested. And it has marginal input, but it's an incredibly powerful spreadsheet to use. It's been in development for over 20 years probably, and it will help you perform this risk assessment fairly easily. So we need to get 10 items on the occupants in the building. Who's in the building? Are they known occupants? How long are they in the building? Do we have transient occupants that we know nothing about? How long are they staying in the building? Short duration or long duration? So we've got just some basic information on occupants. Now, on the mechanical side, once again, we need 10 parameters. We need to know what type of mechanical system there is, where the supplies and the returns are, and there we're getting into airflow issues. So next slide, please, Cassie. So what we're trying to do is rank these spaces from what space do we really need to pay attention to what space do we not need to pay attention to. It's negligible risk, and so we were trying to rank these spaces. Next slide, please. So the result of this spreadsheet is this. You have your different rooms, and this is just a snippet off of it. You can see we have at the training center room, the space A101, and it's a high risk type of space. We need to pay attention to what are we going to do in the space to mitigate or make it a little bit safer than it is currently. And you can see the conference room, it's also a high risk space. We have people coming in, we don't know where they're coming from, we don't know if they're affected or not. So we got these two spaces that we really need to pay attention to. So let's go to the next slide, please, Cassie. So here's a snippet of that spreadsheet. And it's not everything. So we have space information, and it's really not much other than square footage and some basic notes. We give a label to that space. So we have 10 occupant risk factors. So are they known or unknown occupants? How long are they in that space for? Cassie? Everything's ranked 1 to 4. Can we, oh, I'm sorry, Cassie, there we go. Everything's ranked 1 to 4. And then there's weighting factors on each one of these parameters too. And I included the last one, the number 10 of the occupant risk factors, because it is weighted the heaviest, aerosol generation potential. Are we looking at a reading room in the library where no one's supposed to be talking, they're hopefully wearing masks? There's really very little, negligible to low aerosol generation potential. Or are we talking about the balcony in a church where people are singing, where we've already had super spreader events at those instances? So that's why that's weighted so heavily. And that's on a different spreadsheet. This automatically feeds into a second spreadsheet and provides you, it crunches the numbers and provides you what the risk in each space is. And then you can see the HVAC risk factors, what type of ventilation system is there, how much airflow is there, how much fresh outside air are we bringing in, things like that. Fairly simple things. Everything's 1 through 4. Shouldn't take too long to fill out this spreadsheet and get that first one that I showed you that ranks those spaces. Cassie, next, please. So here's that floor plan that we were looking at. So we see on the right side there, that red space and the conference room next to it in the orange space. These are high risk spaces. So we had 4 different mechanical units here, and let's look at this vertically. Let's say the mechanical system on the far left. Well, we've got that one yellow space in the corner. What do we do if we own this building or we work in this building? We might want to tell that person, hey, you know, why don't you work from home? Or maybe that person wants to work from home, and all of a sudden that space turns green. We really don't need to do too much to that space. Now, Ty's recommendations of the 800 ppm are very good. There's a lot of evidence that points to that we should be going below what ASHRAE recommends at 1200 ppm. The mechanical unit on the right, well, we might have to make some changes, or we might want to think alternatively. We need to think outside the box sometimes. That training center in the top left corner that's red, well, maybe we just do our training online, you know, and get rid of that red space. Or we remove half the tables and reduce the density of people in that room to change the risk factor in that room. So it's not always mechanical rated. There's other ways to mitigate the danger in a space or the risk in a space. Next slide, please, Cassie. So moving on to airflow, and this is a really critical topic. Room air does not mix evenly. We really don't know how that, we can visualize it through computer simulations, but you know, in actuality, that's really the only way we can do that. The consequences of not mixing thoroughly in a room is we can concentrate contaminants in space in areas of that room that we don't know about. So the air movement is difficult to predict, but we can use computer programs and possibly tracer gases to figure out, well, how does that air move in the room? So next slide, please. So here we have the same room. On the left side, we have your typical diffuser that sends air into the room, bounces off the walls, comes down. You know, the diffuser, if you look up at the ceiling, you're probably looking at one now. It's to try to mix the room air properly to maintain comfort in that room. But what we're doing with that type of diffuser in this situation is that infected person is spewing out, releasing aerosols, and those are now getting entrained into that airstream, and soon that entire room is contaminated. Now, on the right side, we've put on a different type of diffusion diffuser, and we're sort of creating a curtain between these two occupants of that room, and we're also drawing the air out in a separate space. Now, it's important to think outside the box sometimes. Maybe there's a window behind that person that's asymptomatic on the right side. Maybe we just put a box fan in that window and make sure that those aerosols don't go towards that permanent occupant in that room. So it's not always, doesn't always have to be complicated, but in this drawing there, this is very effective by possibly relocating return airs down below. So we're drawing those aerosols down. Okay, next slide, please, Cassie. So here, this is a diffusion, a directional displacement to diffuser. You can actually change the direction that the air comes out through that. They're about $200 to $400. Sometimes we may just want to move furniture around so that we can put, say, the permanent occupants, like on the left side, left image, we can put that person on the right beneath that airflow and make sure that those aerosols don't travel towards them. Next slide, please, Cassie. So this is some fascinating work by Dr. Kankari. You have the room, one room, the top left is a room with 2 exhaust grills. On the bottom left are 3 exhaust grills. Now, if you look at the right side top, you see the room with the 2 exhaust grills. This is using CFD, computational fluid dynamics software, to model how that air moves around inside that room. You can see that that center person, there's 3 people there. That center person is infected, and after 12 minutes, there's a cloud of contaminants enveloping the person to the right of him or her in front of them. And you really can't predict some of this stuff. If you look at the bottom right, you can see now when we introduce 3 different exhaust grills, oh, well, that person is now in a much safer space. And those contaminants are moving in the direction we want, more towards those return air grills. So it's very important to pay attention to where your supplies and returns are, and basically how many there are too. Next slide, please. And this is just the cloud contaminant. There are actually videos of this showing it time step. And they're just fascinating to watch how that cloud moves through that space. This is all using CFD software. There's a very interesting, Ashley's got a very interesting course on that. You can see a link to that down below. Next slide, please, Cassie. So airflow patterns matter. They're very critical to think about. Next slide, please. So there's all kinds of mechanical modifications we can do. We can increase ventilation. I will include a link to a webinar that Mr. Smith gave me, and it's very interesting. It kind of supports some of what Ty was talking about too. He modeled a room, and this was, well, it wasn't modeled. They actually conducted experiments with tracer gases. It was a laboratory, and they went from 2 air changes to 2, 4, 6, and 8. And the best removal of those contaminants was at 2 air changes per hour. It was just an absolute mess at 8 air changes per hour. And just from 2 on up, it got significantly worse. So is more better? No, not necessarily. You need to be very cognizant of how these contaminants are being distributed inside a space. So, and the pressurization controls on the bottom side, those are important too, because you could have an office with just the supply and then the return could be out in the hallway. Well, we're at a negative pressure outside that hallway door and a positive pressure inside that office. where those contaminants can go, where they're going to migrate, right out in the hallway. So next slide, please. So we have other dedicated filtration systems that Helen or Ty mentioned. We've got dedicated exhausts that we could use, possibly, you know, like something as simple as a box fan. Localized filtration, Ty and Helen talked about that. UVGI, next slide, please. The behavioral are the big unknowns. How responsible are our building occupants? So these are just some of the examples of HEPA filtration. Some have UV integrated into them, some of them then don't. Next slide, please. Well, and here's UVGI, just different examples of it in the mechanical system, or actually up on the wall at the far left, as you can see in a hospital, or roving robots, which are very expensive. You can program floor plans into them. They can travel around. Very effective at cleaning, much better than wiping down surfaces. Next slide, please. UVGI has room in it. At first I thought, no, you know, UVGI should be in hospitals and clinics and things of that nature. I've changed my tune on that. So there's a very good presentation from ASHRAE by Dr. Bonfleth. That's the top link. NIST has got a very interesting presentation too, and then just ASHRAE handbooks have got a lot of other information too. Next slide, please, Cassie. So you have to have, Ty talked about this, you have to have the proper density to kill the virus. Too low and it's going to be effective, too high and it's going to be, you're just wasting energy. And what shocked me in this presentation was when they said that UVGI can be far cheaper than increasing airflow. And that kind of shocked me, or it may be. This is something you might want to look at in certain spaces. When I read that, I thought, well, what is the root of the problem here? The root of the problem is the virus. We can either add a lot more fresh air, dilute it, and try to exhaust it out the building, or we can kill it with UVGI. So UVGI has space in a standard building, something beyond hospitals too. Next slide, please. So don't overventilate. That is very critical. You know, you're going to waste a lot of money if you overventilate, and you have to think about where that air is moving around in space, inside the space. ASHRAE has some very good guidance there at that link below. Just a wealth of information on making buildings ready. Next slide, please. Next slide, please. So in summary, we want to create safer environments. We'll never make anything really perfectly safe, but we can make them much safer than they are now. You need to really think, you need to identify the high-risk spaces. No, we probably don't need to look at every space in a building. Now that's going to change from building type to building type. An office building with limited access, you may be good to go as long as everybody is responsible that comes in there. A school, well, that's a whole different animal. Examine airflow patterns, institute prudent mechanical and control system changes, and don't forget about energy efficiency. We're not going to solve the problem by just throwing more energy at it. So I'm sorry I had to talk so fast, but we're running very late. So you will get the slide deck, and there's a lot of information that you'll get on top of the slide deck too. So thank you very much. Cassie?
Thank you very much, Robert. Such good information. And I did also note in the chat, if there are topics that you're interested in learning more about and diving into, we can certainly have another event and dive further into these topics with our esteemed speakers today. So this doesn't have to be kind of the end of our time together. We can continue the conversation. So I do want to share the contact information and phone numbers for our speakers today. I've gotten a lot of messages so far on CEU, so please let me know if you're interested. And then if you're also interested in working with our team on a risk assessment or building a mitigation plan for your facilities, please feel free to reach out to me, give us a call, or visit our website at cdac.org. We're happy to help. So thank you so much for joining us today. This webinar is recorded, so this will get sent out to all attendees. But now we have a whole host of questions. So I'm going to ask a couple of our team members that are panelists on this on this session as well. So Sean Maurer, Todd Rusk, and Brian Deal are also a part of the CDAC team. Todd is our Director of Operations, Brian's our Executive Director, and Sean is one of our senior energy engineers. So our team is here to help answer your questions. So first question we have is a simple one. Robert, are you able to share that spreadsheet that you mentioned in your slides with the group?
Yes, just this morning, Mr. Smith very kindly gave me a version that he said I could distribute. Yes.
Oh, wonderful. Great. That's the easy question.
Yeah.
So I have another question. Do you have any photos of the before and after conditions of campus AHU that were inspected or corrected? I think that this is directed at Dr. Wynn. Often the AHU cooling coils are like a rust bucket, including cooling coil and the drip pan. With combination of different virus that have these been removed, or with a combination of different virus, have these been removed? How has that been accomplished?
So, so the removal based on a few things. So one way is filtration. So that depends on the size of the virus. So the SARS coronavirus 2 has the size of around 100 nanometer. Okay, so but remember that when the virus is released from a human body, it is coated by bodily fluid. So it's not actually you want to remove 100 nanometer particles, but it will be in around a micron size because it's coated with other things. So that is about physical removal. For biological or chemical removal, then it's more complicated because it really depends on the biology of the virus. We work with a lot of virus in my lab, and actually coronavirus is not the most persistent virus. It's not that difficult to remove them. And that is exactly the problem because for the virus that is more persistent, we have immunity. For the virus that is just present for like a few days or something, it's more contagious since we don't have immunity. So so this virus here is an RNA virus with a very long genome. So UV work very effectively with coronavirus because you just have to chop and cut the genome at some locations.
Great, thank you. Next question, do electrostatic precipitors help protect against SARS-CoV-19?
Can you say it again one more time?
Do electrostatic precipitators help protect against SARS-CoV-19?
So I think this is a method for like general particulate matter in the air. So it's I am not aware of any study that use this method, but I expect that it will just work like other particles, airborne particles.
I think we would have to know more about the electrostatic and the charging activity if that's going to work. I haven't heard anything about electrostatic methods.
There's just very few studies in filtering viruses in virus filtration that I'm aware of. One that's just very recent in the most recent ASHRAE journal from some folks at Honeywell, which makes filters. And then a study from a couple years ago by Brent Stevens at Illinois Institute of Technology, where they had kind of a respiration coughing machine, putting various droplets, viral laden and bacterial laden droplets into the air. Very fascinating study, but into a residence scale facility, and then looking at filtration. But with electrostatic, I haven't seen that yet.
Thank you very much. Okay, I have a question regarding UVGI. The location of the lights seem to be different in different systems. For example, the length of time pass. If a building is doing number 1 and number 2, how necessary is UV, especially if it's not industry standard at this time? Ty, I think that was in regards to
Yeah,
your
so
slides.
so UV has been around since the 1930s with studies showing its effectiveness at killing bacterial as well as viral, disrupting their genetic materials. And in our list of responses to pre-webinar questions, I've put some references in there along with what Robert just showed with recent webinars on UVGI. But I think while it hasn't been standard, I think it's becoming standard, and the UV bulb suppliers that we work with, their phones are ringing off the wall, and we're weeks delayed in getting bulbs in. So people have picked up on it. Wherever you can put them in, just a couple of guidelines, and Professor Bonfleth's webinar from ASHRAE that we cited is an excellent resource. Aluminum ducts are much better than galvanized. For sure, you don't want plastic or flex ducts. The UV will destroy them. But wherever you can get them into the airstream, and roughly that 0.02 watts per CFM is a good level, a practical level, an economical level of UV. And putting in aluminum ducts, aluminum reflects 95% of the UV wavelengths. And so you get much better kill efficiency, where like galvanized and steel only reflect about 50%. But however you can get them in there, if they can also see your cooling coils as well as drain pans, there'll be some additional killing of microbial matter there, as well as it's been shown to, this was again by Dr. Milton, who I've cited a reference in our responses, who studied UV in a large-scale building experiment, but that it also seems to disrupt or disable endotoxins, which are bacterial fragments that are very toxic and good to minimize.
Great, thank you, Ty. Are schools tested for air quality as a usual practice in your experience? Does anybody have any information on whether schools do regular air testing or not?
No, not to my knowledge.
It varies. Some schools have more advanced BAS systems that have CO2 monitoring in spaces, but that's usually relegated to newer facilities. Older schools definitely don't have regular testing that we're aware of.
Thank you very much.
Sean mentioned, the building automation control systems or automatic control systems. One thing that people think about is demand control ventilation for regulating the amount of fresh air in a space. Many of the systems that are out there, they monitor and measure at a mixed point of return, which is averaging a very large space. And this is how it's done in common practice. So if we're going to be thorough and thoroughly careful about how we're applying that approach, we're going to have to monitor the CO2 level in many more spaces in the building, and not just an averaged, like an HVAC return type system.
Wonderful, thank you very much. Okay, so I have another question. How is the ASHRAE standard reflected in the number/volume of air changes per hour in a room? How the CDC recommendation that is 80 to 100 outside air should be included in the building space, and outside damper open to 100%?
So I'm not sure if I'm clear on all the aspects of that question, but for example, like isolation wards and things like that may have 10 or more air changes per hour, maybe no recirculation. The University of Nebraska facility that Professor Wynn cited exhausts only without recirculation, as I remember, with HEPA filters for the exhaust. Comparing that to a home which is all over the map, from like 0 changes per hour to like bedrooms, which we've measured are frequently as high as 3,000 to 4,000 parts per million of CO2. So even though in a, say, conventional construction that's not so well sealed, much better than it used to be, but that you get in certain areas of the home and they're very well sealed, and if one child is sick, the other one's definitely going to get sick. So as you look at changing fresh air, I really think CO2 is your easiest way. Anybody who's tried measuring 10, 20, 50, or 100 CFM coming out of a register, it's just very, very difficult. And so carrying around or getting one of these simple monitors, like Professor Wynn has shown, that you'll become much more aware yourself, and can just kind of see the fluctuations, and then hopefully figure out what you can do with your systems to take care of that.
I would also add that some of the very generalized recommendations sometimes come from a place of abundance of caution, which in these kinds of times is appropriate. But so we apply general rules when we assume that the general population receiving that message doesn't understand all of the application details and all of the some of the nuance about airflows and ventilation. So I think when we have sometimes there will be situations where that has to happen. We come back to the point about energy efficiency. If we are just opening up everything and running airflows, we can see 50 to 100% or more increase in energy costs. And in some of the example that Robert cited, we can increase airflows, and what could happen is we increase the turbulence of airflows in this space, and we actually increase the level of dispersion of these particles. So we have mass guidance, which can help in the abundance of caution. But if we have a little bit more information and ability to apply nuance guidance and a little bit more targeted expertise, then that will be a better situation.
Thank you, Todd. And I think this kind of follows what we were just talking about, and it refers to the library example that Ty mentioned. Ty mentioned that outside air was contributing to humidity issues. Most engineers are designing ventilation to code requirements. How do we reconcile these diverging requirements?
Yeah, so a lot of the initial guidance was, open outside air dampers to 100%, bring in as much outside air for dilution as possible. And especially in our climate where we've got hot, humid weather and exceptionally cold weather, there's a definite possibility with a system where if you followed that advice, you would overwhelm its ability to maintain temperatures within the building. So you got to kind of temper your actions with what your system can handle, which is where that 800 parts per million demand controlled ventilation setting or CO2 tracking comes in very handy. Is it's kind of a nice midpoint. It gives you some control of you're recirculating some of your inside air and blending it with the outside air so that your system can keep up and maintain temperatures, but you're still increasing ventilation enough to provide adequate dilution of viral particles and indoor air contaminants.
One thing I'd like to add to that, Sean, is that it really depends on where your CO2 is being measured to. Our demand control ventilation systems rely on a single point of measurement in the return air duct. Other times it pulls. CO2 sensors in different spaces. So if we have a single space, a single point where we're taking those measurements, we may still very well have spaces that go well over the 800 ppm. So the advice from Helen and Ty about individual little gadgets that we can take from monitors from space to space and measure the CO2 in those spaces, that's good advice, because most systems are not polling every space in the building to see what the ppm is, the CO2 levels are.
And I might add that, for example, the ventilation system that we manufacture for residential applications, but we have battery-free wireless technology sensors that are placed in every room that monitor CO2 temperature, humidity. And a house is pretty complex because it's part restaurant, part hotel, part meeting space and recreation space. And sometimes it's occupied, sometimes it's not. And so homes are very dynamic spaces, but with today's technology, these sensors you can paste on a wall in every room, and each one is chirping back to our base system what that local air quality and comfort condition is. And then in a number of homes, it's like two old people like my wife and I just shuffling about the home. So the pollution cloud's moving with us and getting smarter about where you're delivering fresh air within a large space. Makes a big difference on energy efficiency, but also helping us to provide healthy air where it's needed most. And other areas that aren't occupied are storing fresh air that can be made better use of. And so these are things that are coming along. They're getting used in buildings, and I think before long will be the standard way we construct our built environment.
And this is a question somewhat similar to airflow. Are there any ways to use HVAC smoke pens or incense to help visualize airflow in a room that don't set off smoke detectors?
Yes. Well, I don't know if they want to set off smoke detectors, but I will provide a link to a webinar that shows actual examples of the distribution of a smoke generation machine within the space. It's better than just trying to draw arrows on a diagram or point to this is where the air is going, so that it helps. It's still not like CFD, but most people aren't going to be doing a CFD type analysis. So yes, you could use something like that to at least help you identify where air is flowing inside this space. It's not going to tell you the concentrations, but you can do that with tracer gas experiments. But once again, you're getting into some pretty complicated stuff.
So I want to jump in on the, I guess one thing to put out there is that there's lots of, Robert mentioned CFD, we're talking about smoke tracing. So for the folks where these things are accessible, by all means, go for it, and that's important. But not everybody's going to have access to this. So I think we have to also accept that we don't have a perfect situation. We don't have perfect ability to model and simulate everything. So I think the idea of thinking about airflows, how can we spread out our airflow supplies and our airflow returns or exhausts? How can we make sure that people are not downwind of others? Our intuitive understanding might not be perfect, but it will be better than nothing.
Thank you very much. Okay, we have time for one more question here. A number of companies have introduced UVC lighting air purifier ducts for HVAC system. Is there a viable option, especially in conjunction with increased airflow capacity? Has anybody heard about UVC lighting air purifiers for the HVAC systems?
UVC is the same one as the UV device that Ty and Robert presented. It's all of them are using UVC at the wavelength of 254 nanometer. The only thing I want to mention is that that wavelength is very good for genome damage. So it will damage any genome, doesn't have to be viral genome. Okay, so that also, you know, your skin cell, anywhere that has a genome, it will damage. So if you use it, make sure you take precaution.
Yes, and I agree. I think you'll find a number of manufacturers for the airflow, and the increased airflow might be more bulbs or more powerful bulbs, but there's a wide array of them available, and there's a lot of ASHRAE guidance. ASHRAE handbook fundamentals and applications have a lot of good details, and the work from William Bonfleth, who us University of Illinois people always like to point out, he's an alumnus from here, but he's a former president of ASHRAE and a professor at Penn State, along with Professor Shelley Miller at the University of Colorado. Those two people have very substantial research studies that they've conducted over the years, looking at filtration versus ultraviolet and combinations to give you the optimal removal of particulates, disabling of microbes, and then good practical guidance on to apply, as well as upper room ultraviolet that Robert referred to.
Great, well, thank you. I know we still do have some questions, but we are going to wrap up today's session. So all questions that did not get answered in today's live session will be answered offline and will be provided to all attendees so that we can get your questions answered in a timely manner. So thank you all again for joining us today. Thank you to our esteemed speakers, Dr. Nguyen, Dr. Newell, Mr. Nemeth. Thank you to the CDAC team for your support in the Q&A section of this webinar. And I look forward to your feedback on the webinar and how we can continue our conversation around safe reopening of buildings in the time of the pandemic. Thank you all. I will follow up with the recording and supplemental materials as soon as possible. I hope you have a wonderful day, and thank you again to all of our panelists for sharing your knowledge and expertise with us. Have a wonderful afternoon.
Thank you.
Thanks.